Okay, we're going to complete chapter 18 with this short video on amplitude modulation and sampling, both of which are practical applications. AM, of course, you're used to that with radio, where you provide signals, largely music and so forth, but it's a concept, amplitude modulation. Sampling is a big deal now because it's really the basis in how we do digital recording of anything, videos, voice, all of that is all about sampling. So amplitude modulation, quite simply, we've got, let me get it going here, what's wrong? Hang on. Okay, well, sorry, we have some time wasted there with technical difficulties. All right, so in amplitude modulation, we've got some signal that will modulate. So this would be my voice right now, for instance, or, you know, some song that's going to be recorded. And it has, you know, some, call it a cosine signal or not. All right, we might visualize it like this. A single sine wave, so not a song or something more complex. And the frequency distribution of this, the transform of it, the frequency transform, shows plus and minus components. Didn't we just look at that in Parseval? Plus and minus components at equal locations. All right, then we have something called the carrier, which is going to take the signal to be modulated, that's going to modulate, and think of the modulation as this is the, this here is the information. Right? Whether that information is a song or it's bank records or anything, the modulating signal, that's the information that we want to transmit. The carrier is the signal that's going to carry it from point A to point B. Now notice right away, just visually, I'm not rushing into the math on this, just visually you see right away the frequency here is higher than the frequency here, right? The carrier is a higher frequency. And when I plot the frequency spectrum of that, I end up with magnitude vectors that are further out. In other words, they're at a higher frequency, okay? And the goal of amplitude modulation is to use this signal to modulate this amplitude. This is what I get. I use this slow signal, here it is, this slow signal modulates this amplitude, which originally is a steady amplitude. Okay, so this is a simple case. One frequency modulating another frequency. The important thing to note is the carrier is a higher frequency. And when I put these two together, I'm just showing you pictorially the frequency spectrum simply says these two lower frequency vectors are attached around a carrier frequency in both the plus and minus space. And notice that. So I want you to have this visual in mind before we get too tangled in the math. Okay? All right. So here we are. This is the frequency of the time domain. It's the carrier right here times 1 plus the time function of the modulating signal. Okay? And this 1 plus is simply going to provide an offset, right? it's not going to bring the carrier in at 0. It's going to bring it in at a little bit of an offset. Well, actually what you've got here is the carrier itself and then a modulating signal attached to that. So this is now the new amplitude, right? That's all I'm trying to say. I'm wrangling around in words here. This is the new amplitude. The new amplitude of the carrier, right? Prior to that, m of t wasn't there. So we just added m of t on, right? They were not multiplied, they were added. Okay, so let's do Fourier transforms. Fourier transform of 1 cosine of t is just the Fourier transform of that, plus the Fourier transform of whatever the magnitude is times this, okay? So that's the Fourier transform of the amplitude modulated signal, okay? And we can now take that apart in pieces. The first part is, what is this? Oh, that's just a delta function of omega minus omega c and a delta function of omega plus omega c, right? What was that? That's these guys right here. That's what's going on with that, okay? So if we take that, so that's part of it. That's the first piece. The second piece is the modulated signal, right? And we have the modulated signal at plus and minus around the carrier, okay? And when you go through the math on this, it ends up being divided by 2. Okay, so here is how that looks then. This is that picture. The text just adapts the one for naming's sake. We call the carrier WC, and WC plus and minus WM are called the sidebands, the lower sideband and the upper sideband. And there are various things you may have heard of: single sidebands, double sidebands. This is what we're talking about. Double sidebands is this. Single sideband is only one. A lot of communications is based on this. You'll hear these terms tossed around and so forth. Pictorially, this is what's going on the frequency spectrum. Okay? If I have a single sideband, that's what the frequency spectrum would look like. Right? It's that area from 0 to Wm of the modulated signal. If I have double-sided, that's what this is. So it's going to cover all of this. Right? You have a range of frequencies in there. All right, now let's go to sampling. That's just a touch of amplitude modulation, but it's very easy to do the math on it in Fourier. So now in sampling, we have two things. We're used to this. This is maybe the modulated signal from before, the low frequency. And now the sampling frequency can be thought of as just a whole lot of pulses, right? So delta functions, spaced equally at some distance from one another of tau sub s. Okay? If I put these two together, in other words, I let this signal, the modulated signal, determine the amplitude of these guys, I end up with this as a time picture, right? And if you could do this in time, you would really be able to see this on an oscilloscope, for instance. Okay, but this is what you would obviously think sampling, using this sample signal to sample that signal of interest. Notice the sampling is a lot more samples than there are this frequency here. You get this, a series of modulated sample signals. Okay, so what's going on with this? I'll just repeat those off here on the side so we've got them handy. But let's take this. Here's our sampled signal. Okay, so there's the signal itself acting as an amplitude, and it's the sum of a lot of delta functions, right? This right here, right? This right here is just the mathematics of that. Okay? And we can write it another way then. We can actually say we haven't lost this. This is carried forward, right? And all we're observing is, wait a minute, if this is sampled, the only thing I care about is the value of G at these individual times. Whoops. The value of G of t at n of t, right? And so if I've only got a bunch of samples and they're subject to n, then just gather them inside. So it's just a way of rewriting it, okay? So here we are. Now we want to go, why did we do this? Obviously we're aiming toward doing a transfer function or doing Fourier on this. So now if we go to the frequency space, we're already just doing a simple sum. We've gotten time out of it. We've gotten time segmented, right? So we have these amplitudes of the function g times the Fourier of the delta function. Okay? Well, that one's pretty easy. We just go back to our tables, 18.2, table 18.2 in the text, and we just look up what it is. The delta function transform is simply e to the minus j n wts, right? And this again. So what are we saying? This transform, let's just mark them up, is this piece right here, right? The rest of this is carry forward. So we just do that transform. There's the Fourier transform for that. Now it's in the frequency space, and we just have as many n's as we need, right? Because this is just the delta function, right? And the transform of the delta function is e j omega t. All right. Now let's go again. Now we've got this. So this is just the author just copies this down here and says, where can we go from here? Well, if everything is a function of some number of integrals of ts, I can just divide by that integral. In other words, I'm just factoring out the time integral. And I'm saying, what do I want here? I want the sum of the frequency specification of the modulation signal G. And I'm just going to look at it at a bunch of times. So what is this now? It's my modulation, my basic frequency plus n times my sampling frequency. And I'm just going to, the sampling frequency is the 1 over Ts, right? So I will then generate a sum of those terms, right? And so cleaning that up, it's just all of this just got dragged down from there. So GS here is now equal to this piece right here. Okay? And all you have to do is remember then that 1 over Ts is the sampling frequency. Right? This is the sampling frequency. Okay? And what this is telling me, and the important thing of all this, is that this frequency has to be greater than twice the highest frequency to be sampled, right? We did all this, and the author does it with a single frequency, and you develop all this stuff as a single frequency. But if this signal actually is, you know, a signal itself, which contains a lot of things, and I'm sampling that, obviously, if I'm not sampling fast enough, like say right here, I catch that point, and the next point I catch is way up here, it's going to reinterpret that as a straight line. But maybe there's a lot going on. Well, we know from Fourier transforms that any signal I have, the sum of a whole lot of sine waves can create that signal. The sampling theorem says if I'm going to catch and accurately be able to reproduce the signal that I'm sampling, I must sample it at twice the frequency of the highest frequency component in it. Now look at this, the original signal right here, this one, and all these little fast bars. It turns out all I need to know is at least 2 zero crossings, right? And if I know those, and I know I'm sampling at least as fast as twice that frequency, then I will catch any 2 points and I'll be able to reproduce a sine wave from it. Okay, but if I don't sample fast enough, if I sample, say, here, and then again down here, right? Let's say I sample here and way over here, I won't know where those zero crossings are. I really need to know, in a sine wave, I need to know the point there and the similar point down here, right? And I need to know the next point, the next good point over here. Okay, I can only do that if I sample at twice the frequency. And if the signal I'm sampling is the sum of a lot of frequencies, I have to sample at twice the highest one. Okay, and that's the key ingredient of what's going on with sampling. And that's why, you know, this high frequency thing is often referred to as, because it is, the Nyquist criteria. But here you can see, I'm just trying to show you pictorially here what is, you know, why that sort of intuitively makes sense. Because the Fourier series says I can represent any signal as a sum of sine waves. And if I can reproduce any sine wave knowing 2 points, and that would be like knowing 2 zero crossings, right? Then I know the frequency of the sine wave. And if I know that, I can reproduce that sine wave. Well, if the highest frequency in a set of frequencies, if the highest frequency is sampled at the proper rate, then I can detect everything underneath it, because that's simply a measure of all the various different sine waves that compose the wave. Okay, so I'm going to end here with the lectures then on Chapter 18, and we'll be back with Chapter 19.